Good morning, and welcome to the EGS Anywhere panel of PIVOT 2020, EGS, Deep EGS, Supercritical, and beyond. Scalable geothermal concepts can enable production of geothermal energy anywhere in the world. If we drill deep enough anywhere on Earth, we could find a resource for geothermal energy. The challenge comes in the form of how to recover these thermal resources in an effective, safe, and environmentally sustainable way. This panel is going to explore engineered or enhanced geothermal systems, EGS, how these systems are created, the challenges associated with reservoir connectivity, integrity, seismicity, with risk and mitigation, and how the application of oil and gas technologies could be leveraged to address some of these EGS challenges. We're also going to discuss supercritical systems, those geologic systems that exist above the supercritical point of water. These have some very unique opportunities. We'll also share some of the challenges with EGS. I'm Rob Pagorni. I'll be your moderator for this session. I'm the Geothermal Program Manager at the Idaho National Laboratory. I'm also leading the reservoir modeling team for DOE's FORGE program, or the initiative, or the process for creating the United States' flagship for geothermal energy research. My research interests center on energy and water-related issues, primarily focusing on investigations of fluid flow, heat transport, mechanics, and fracture networks, and development of massively parallel simulators to describe these systems. I've been focusing on EGS for nearly the last decade, and I'm very excited to see all the attention and progress geothermal has been making of late, and I'm very happy to be part of PIVOT 2020. I've been very vocal that geothermal needs to jump the technology development curve and take the learnings from oil and gas industry with shale gas and apply those to geothermal energy development. Many thanks to the PIVOT 2020 organizers for making this important step to bring these two worlds together. And with that, I'm going to please let me allow my panelists for this session. My first panelist is Vic Rao, the Executive Director of the Research Triangle Energy Consortium and the former CEO of Halliburton. Susan Petty, the President and CTO of Altarock Energy and the CTO of CERC Energy. John McLennan, a professor at the University of Utah's Chemical Engineering, and is also, with me, the co-PI, the principal investigator of the Utah Forge EGS project. Isabel Shambefort, the senior geothermal scientist with GNS Science in New Zealand. And lastly, Mukul Sharma, the professor and chair of the Hildebrand Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. I'm going to give each panelist 2 minutes or so to discuss why they think this is important, why they're part of this PIVOT 2020, and tell us a little bit about themselves. So with no further ado, Vic, I'll turn it over to you.
Okay. So as he mentioned, as Robert mentioned, I retired as CTO of Halliburton a dozen years ago. Since then, I've been advising folks, especially startups, and writing books and things that retired people do. Let me get into what brought me to So I'm a new entrant into this geothermal arena. I used to be a skeptic. When at Halliburton, I pretty much thought it was very niche place, and I essentially discouraged my folks into looking much into it. Most lately, I've seen the advances in it and now think it is scalable. Before that, my real problem was I didn't think it was scalable. And I now think we can get utility scale dispatchable electricity. In the full interest of disclosure, I advise an EGS outfit called Fervo Energy and a closed loop outfit called Sage Geosciences. So while I do not expect that to color my thinking in too many ways, my remarks in too many ways, you need to know that. And I'm not going to take my 2 minutes, but somebody else doesn't have to take my 1 minute.
So thanks, Vic, and thanks for that nice introduction. Susan, I'll turn it over to you.
Great. So I'm Susan Petty. I'm the CTO of CERC Energy, which is a geothermal project operator and developer. We have 5 operating geothermal power plants in the Western US. And I'm also the founder, president, and chief technology officer for Altarock Energy. And I've been in the geothermal business for 42 years. A lot of that time has been focused on stimulating, fracturing, creating geothermal reservoirs through using methods that are and were typical in oil and gas and have been used in unconventional oil and gas plays. So I've started out with the first well that was drilled on the Big Island while I was a graduate student at University of Hawaii. And I've worked all over the world on geothermal energy. I also was involved with the Fenton Hill project. I did stimulations at the Baca Grande in New Mexico and East Mesa field. Many of the early fracturing efforts that were funded by the US government. I was also involved with the Eastern Shale Gas Project. You can now tell I'm pretty old. So, currently Alterock has changed its focus, not away from fracturing. We're still wanting to do that, but we are really moving towards going to very, very high temperatures to increase the energy density of the resource that we're trying to tap, and to get to the point where we can have very, very high electric conversion efficiency, which we hope will bring down costs dramatically. So that's where we're headed.
Thanks, Sue. We'll come back. Let me transition to John McLennan. So I would just, in prefacing John, I would say, John and I both work on the Utah Forge project. We lead different aspects of the program, and we disagree on almost everything. So we always have very colorful discussions. And so hopefully you'll see this continue today. John?
Well, Rob, thank you for that kind introduction. As Rob mentioned, my challenge on Forge is to drill 2 wells and interconnect those wells with hydraulic fractures. And my background in order to do this is that I started my career working on a PhD that was related to Fenton Hill. I was lucky enough to actually participate in some of the fracturing on Fenton Hill. And then I took a 30-year diversion to the oil and gas business and moved back to geothermal, working on Raft River and recently on Forge. And what strikes me along the way is the room for collaboration, for joint development, and also some of the philosophical differences that exist between the geothermal industry and the oil and gas industry. And so, like Vic, I'll give up 1 minute of my time for the common good.
Thank you, John. I'd mentioned that, much like a congressional hearing, if you yield your time, I take it back and we'll distribute it later. Isabel, let me hand it over to you.
Hi, so I'm Isabelle Chamfort. I am a senior scientist at GNS Science. I am leading the newly founded program called Geothermal the Next Generation in New Zealand to explore possible supercritical resources here. So this is a really exciting time. I am as well the project leader under our New Zealand Geothermal Future, the project leader of high enthalpy research. And I have a little different background compared to the rest of you. I come for actually ore deposit research. And I moved 10 years ago when I moved to New Zealand. I moved to geothermal, and the reason was I wanted to have a better effect on the planet, and having something that is a bit more linked with the needs of the community as a whole. So yeah, that's about me. My main interest is looking at what's happening when you're drilling closer to magmas, and what are the geology associated with that. So I have a very geological academic background, if you want to say. Another thing that is really close to our heart here is to actually communicate about geothermal and communicate about the science we are doing to enable, obviously, in the future, the development of non-conventional resources. And that's about it.
Thank you, Isabel. Thank you so much. Last but definitely not least, Mukul.
Yeah, thank you, Rob. So I'm Mukul Sharma. I've been involved in the oil and gas side of the business and also in the geothermal side a little bit for the last 40 years. For the first, back in the 80s, I was involved in some early work on geothermal, and I left the geothermal business for about 30 years. working primarily on reservoir modeling and reservoir engineering, and then the last 20 years on working on hydraulic fracturing, modeling, as well as doing some experimental work. I lead a joint industry program here related to hydraulic fracturing, which is funded by most of the oil and gas companies in the US and abroad. We have been working primarily in looking at unconventionals in the last 15 years or so. And I will say that we've learned a lot in the last 15 years in how to fracture wells, how to do things a certain way in horizontal wells and fracturing and so forth. And so my interest in geothermal has arisen from my background in fracturing and horizontal drilling. And in fact, if somebody had asked me about 10 years ago what I thought of geothermal, I would have said, like a lot of people would, that it was a niche application, a niche energy source that was struggling to be commercial. But I think given what we have learned over the last 15 years in how to complete these wells, I think there's a real opportunity in applying all our learnings from the oil and gas side towards geothermal. I will say that EGS systems compared to closed loop actually can really dramatically lower costs in many ways. And we can talk about this some more, but and there are lots of technical issues and social issues associated with applying hydraulic fracturing in geothermal systems. And high temperatures, how do you get good connectivity between fractures? How do you get profile control in these wells, and what kind of proppant should be used and so forth? So I will hold off on that discussion as the questions come in, but I will stop there.
Thank you, Mukul. And you mentioned the good things as the questions come in. So just for some housekeeping, if you're interested in asking a question of the panelists, there is the Q&A or the question part where you can actually submit a question. We have moderators looking through those things, and they'll feed them to the panel, feed them to me as we go. We do have some prepared questions that we're going to start with, and then as we go through a few of those, we'll start entertaining questions from the audience. So please have the questions coming. And I would always say we don't get them all answered on live today. We can keep this discussion going in other means later. So I'm going to take as I'm the moderator, I will take the bully pulpit and take the liberty of asking the first few questions. And the first question asked goes to John McLennan. John, as the lead for the well design, drilling, and completion for the Utah Forge program, what is the one biggest hurdle that you that you're currently facing, and how are you approaching the solution?
Just one?
So your highest one, yes.
All right. The immediate issue is drilling a high angle well in a material that typically has rates of penetration that are less than 10 feet per hour, and applying directional technologies to the geothermal industry. There have been some cases where geothermal wells have been drilled at moderate angles, but I think we're all interested in applying, certainly in these medium temperature rocks, PDC bits, directional control, measurements at the bit, and drilling these holes and safely and effectively running and cementing casing in these wells. That's my immediate challenge.
That's all. Okay. But cool. Do you have any comments on that? What are your thoughts?
Well, I think John said it well in terms of where we start, which is drilling these very hard rocks at high temperatures. I mean, that certainly is a challenge. There's no question about that. But on the fracturing side, I would say that getting good connectivity between wellbores in a predictable way, and ensuring that if you were to use long laterals, having a uniform distribution of fluid across the entire lateral, I would rate those as the two biggest challenges on the fracturing side.
Thanks, Mukul. And actually, I think, Sue, you've had some very practical experience in doing some of these EGS stimulations. I'm going to ask you to kind of weigh in here. but I'm going to take the liberty of saying a few things myself. So Mukul, you mentioned something that I've been thinking quite a bit about, and that is getting equal distribution of fluid out of a long reach lateral with a multi-stage stimulation. We're not talking about it now, but I want to talk a little bit about some limited entry techniques that are pretty common in oil and gas that could bring strong to bear for geothermal, especially in how we do some completions. But so, will you weigh in for us here from your experience? I know very detailed where we've spoken in the past.
Yeah, so on the issue of directional drilling in geothermal, I mean, we directionally drill all our geothermal wells pretty much, and some of them have very, very high angle. In the geysers particularly, we have long reach wells. We tend not to go 90 degrees just because we don't have to, and it's expensive to do it, but we have done that, and we do sometimes do, very, very high angle, 75%. Wells, so that's doable. PDC bits, yeah, that is a real serious issue. PDC bits at high temperature are not, in these hard brittle rocks, are not that great, and definitely need some work there. On the fracturing and connectivity, that's an issue in the past because we tried to drill 2 parallel well bores and fracture between them. And one of the issues we run into, particularly in geothermal, is that with depth, the stresses tend to change. And we see, stress measurements we make up at a shallower depth may not, reflect the real stress situation at depth. So we now drill, when we do EGS stimulations, we drill 1 well, and then we fracture and map the fractures, and then we drill into them. And because we do have good directional control, even in these hot rocks, we can, direct our wellbore to intersect as many of those created fractures as possible.
Thanks, Susan. Vic, you mentioned in your opening comments, about scalability and some skepticism. So how scalable do you think geothermal could be, especially in the context of an EGS system? And what do you think? What's the key research that needs to be done to ensure that we can get this deployable at industry or commercial scales to make it impactful?
Yeah, I think so. I'll go with EGS since you asked for that. And for EGS to be successful, what we need, the industry needs, is subsurface mapping of temperature versus depth, and also responsive to something Susan said. One of the things that makes it easier to get fractures to propagate is if you intersect natural fractures. So EGS is much better off when it intersects natural fractures. So mapping of natural fractures worldwide, mapping of temperature versus depth will be needed. Then for closed loop, basically what will be needed is improvements in cost. And then finally, on the mapping deal, this is an analog with geophysical, okay? And I wouldn't be surprised if people think this is going to take off, that companies step forward, do the mapping, and just like it happened in geophysics, make libraries, do it in spec, do some custom shoots, make it available to each other. That's what's going to proliferate it. And I think we need those players as well, not just the people who drill.
Thanks, Vic. You mentioned something about getting players to come into the game, and when we talked about some of the introductory remarks when Isabel mentioned she came from an ore deposits and that kind of thing. But I think of it a lot of times the economics of geothermal systems to be more akin with economics of minerals. Because in general you see margins are tight and things are small, so which I think is a kind of a large departure from the normal economics we look at from the oil and gas industry. So what do you think here? Because your role in working for an energy company, a producing company right now, how does that economics work out for you guys? And what do you think the path might be from what Vic was saying?
Well, CERC's strategy has been to acquire pre-existing projects that are in distress and treat them as fixer-uppers. So we tend not to do a whole lot of exploration to find geothermal resources, but we do use the technology that Alterock has used in the past to stimulate wells. So if we have a field that has hot wells that are in tight rock. We do use stimulation technology to improve them. So what we see is that the economics of these projects is really dependent on the temperature and flow rate you can get out of each well. And particularly at the low flow rate, at the low temperatures that CERC's projects operate at, we need really, really high flow rates to make this work economically. But yeah, we're going 24/7. We're looking at thermal energy storage to help improve our economics.
Thank you. Let me transition a little bit. So we've been talking, temperatures came up a few times, and we've been focusing, on EGS technologies, and we're going to come back to it. But Isabel, with all this, there has been some considerable attention in supercritical systems. What do you think the role there that they could bring into bringing more geothermal forward to the forefront? What do you see? Are there different challenges that we're facing, or what are similar challenges that compared to EGS and vice versa?
Yeah, as you mentioned, there's a lot of supercritical projects. I mean, a lot. Where the challenge, the first challenge is that it's probably not everywhere that you can develop supercritical science and supercritical reservoir. One of the biggest challenges as well is to combine, if we found supercritical fluid, is to have a well that is, viable, basically. And that you can maintain. Some of the wells that we have, the first one, for example, IDDP1, was lost very quickly, and for several reasons. Is that when you're going very close to magma, and you have a lot of corrosive fluid. So it's a lot of engineering development that is happening right now in terms of casing stability. One of the things as well that needs to improve is the design actually of how you're utilizing such a powerful fluid once you're getting at the surface. So again, there's a worldwide investment into that space. In terms of drilling, which is not necessarily where I'm really clued in, but obviously, because you're going towards high temperature, everything is a little bit more challenging. We don't have all the downhole tools that you will have in EGS or conventional geothermal. We can't apply the same thing, I would say, for the drill bits. So everything needs to be upscaled for temperature that can resist almost 400 degrees. So there's a lot of challenges. The Icelandic have been doing really well and doing this. Japanese as well are going. There's really a worldwide push, because if we manage to get that, the return in energy, if you want, that we can have is going to be terrific. So yeah, that's. I mean, as people around, if you have something to add on, Susan, maybe on actually the drilling technology, that would be great.
That you mentioned, there's a lot of things you mentioned there. Thank you for that. I find it, the one thing you said near the end was energy, the energy density that we can get from supercritical systems. And I think that is a key thing that could bring people in. I know, Sue, you have a comment, and also I want to transition and ask and push a follow up to Vic as well. But Sue, please weigh in.
Yeah. So one of the things that we've focused on is getting to supercritical temperature rock, and then fracturing it and introducing, fluid to that in an EGS system at supercritical temperatures, because indeed, as Isabel says, the supercritical natural systems, the fluids are very, very challenging. I mean, I've worked on supercritical systems in Indonesia, in the US, and it's really a challenge to produce those fluids. But we're hopeful that if we can do an EGS project where we're introducing fluid from the surface, that we can get around some of that where we don't have the magmatic gases. And on the drilling side, when we get up to these very high temperatures, one of the things we've found is that our rate of penetration tends to go up. I think we're doing a lot of thermal fracturing when we drill these wells.
Thank you very much. But you mentioned that the could be the potential corrosivity of the fluid and some of those challenges. Vic, that kind of comes back into some of the things we were saying earlier. Even for a closed loop design, What do you see there? How we can apply, essentially, 400 degree C thing in the bottom hole well temperatures or higher? Are there particular challenges there? I'm thinking through like materials challenges, in addition to accessing the reservoir, but actually having some standard technology that we can actually use to have it sustainable production.
Yeah, so let me use a time-honored technique of answering the question I want to hear. I think that EGS at 200C is going to be very effective if you know what you're doing here, because water is a wonderful transmitter, is a wonderful conductor. Closed loops in general have the issue that you don't get thermal conductivity. So you got to go to supercritical in order to make closed. Well, I shouldn't be that categorical, but I think you have to go to supercritical in order. Supercritical means the water in the supercritical state, which is a heck of a lot of pressure and temperature. So, and you deal with materials of all sorts. So I would say that EGS at 200C is something that will proliferate long before supercritical closed loop becomes economically viable. And I think as far as the drilling goes, I'm not afraid to drill horizontal wells at 200C. It depends on the rock. Not all rock is basalt. There's a lot of sedimentary rock at 200C. So we'll get there. And if the oil industry steps up and says, let's solve this problem, then some of these issues go away. And finally, to the point that John made earlier, measurement while drilling is difficult. Well, geez, we are strapping fiber optic cable to the casing, okay? And so we can do a lot of measurement, which is different from normal MWD. So these things can be solved.
Thank you. I just want to thank the audience. We're getting a plethora of questions coming in. I have some additional prepared questions. I'm going to pose one more, and then I'm going to dive into some of the audience supplied questions. So Mukul, I want to take a step back and think about things in a more general sense. Why geothermal? Why now? And from an oil and gas perspective, what do you think the biggest impact on a geothermal/oil and gas partnership can have in the immediate future, in the next year, the next 2 years? Can you share your thoughts on that for us?
Yeah, I think what really changed my opinion was that we've traditionally done geothermal with deviated or vertical wells with single fractures or maybe 2 fractures and a relatively small number of fractures. Whereas what is possible today with putting in 100 or 200 fractures into a single well, you could get contact areas between the rock and the fluid that were an order of magnitude larger than what we were able to achieve before, at least an order of magnitude larger. And that really does transform the way the energy recovery rate that you can achieve in these wells. So to me, that could be the game changer in the future. Now, we still have to work on a lot of technical issues before we can actually claim that we achieved that. But I think, in my mind, the ability to create large surface areas that we could circulate fluids through is the central point that really drives me to believe that you can actually achieve much larger efficiencies, much larger heat recovery rates than you could in the past. And I think we know how to do that primarily from learnings from the oil and gas sector that we've learned over the last 15 years. And we didn't know how to do that very well, 10 years ago even. So I think we've learned a lot in the last 10, 15 years.
So John, I'm gonna kind of pivot back to you. Mukul mentioned technical issues, and if anything, if everyone's going to find a technical issue, it's going to be us working at the Utah Forge program. We're actually at the forefront trying to do some of these things right now. So can you weigh in here just briefly? Sure.
One of the common themes is creation of surface area, but in order to be able to create the surface area, it also requires an effective isolation technology and an effective cement job. I think that this is we sometimes forget this, and we can learn a lot from the supercritical business just in terms of metallurgy counts, even in the lower temperature stuff, metallurgy counts, and an effective cement job prior to hydraulic fracturing may be one of the most critical elements. And we're really learning this from the oil industry of late, who have found substantial difficulties in terms of casing collapse and degradation of pipe associated with extensive fracturing. So I say you need the surface area, but you need the underpinnings to be able to do those fractures effectively. And in terms of that, that may have us re-looking at some of our cementing in terms of the effectiveness of foam cement that we've done in the past that may really not be living up to spec, and we really need to evaluate cementing significantly.
Thanks, John. And I would mention, as you were speaking, I'm watching all the other panelists, and you got a lot of reactions there. So first, I'm going to transition to Susan, and I know because I saw her kind of moving her chair when you said something. Vic, I'm going to come to you next. So.
Okay, so there's a reason that we do not do cement and perforate completions in geothermal, and there's also a reason why our well bores are so much larger than the well bores typically drilled in oil and gas. In oil and gas, one of the most common bit sizes used is a 6 3/4 inch bit, and in geothermal, our most common bit is a 12 1/2. So we drill big wells, and we do not cement and perforate in our completions because we need to flow really, really high flow rates to make these low temperature, lower enthalpy fluids. And I'm talking about temperatures up to 225 C. So in order to make that economic to produce, we need to produce really high flow rates. And you kind of can't do that through a cement and perforate completion and a small well bore diameter because you have too much pressure drop and you have to pay for pressure. That's something you just have to do. So we have gone to large diameters. We've gone to completing either open hole or with perforated liners. Now in oil and gas, you can do multiple stimulations using sliding sleeve devices in the open hole, and that is something that I really think we're going to need to get to. On the other hand, John is absolutely right. A good cement job is absolutely crucial to the long-term stability and viability of your well, particularly at very high temperature. Being able to withstand the thermal stresses that come from thermal cycling, and particularly if we're talking supercritical temperatures, that is very, very tough. So we need to look at our materials, we look at our well designs to be able to design these wells to last if we're going to go to high temperature.
Vic, what are your thoughts?
Yeah. So I was going to say that I'm not afraid to drill and complete a 200 C horizontal well. I'm not afraid to put multi-stage fractures. I'm not afraid to make sure that you get the flows through the clusters you want to. These are, if they're not straightforward, they can be straightforward if the industry steps up and says, we will make this work, okay? And see, for example, one of the embodiments is when to connect between the injector well and the producer well, you have to have the fractures connect. You can take advantage of what the industry has learned, which is frac hits. Frac hits are bad in shale. They are good in geothermal. So the industry learned stuff that makes me not at all concerned with multi-stage fracturing in 200 C.
Very good, very good. McCool, I saw you raise your hand, or
well, I was just going to add. I was just going to agree with Vic. I think that there's when we frac wells, we inject at 90 barrels a minute. Okay, that's over 100,000 barrels a day, and so you can certainly go at very high rates, and you can certainly frac at 200 C. We know how to do that. We've done it before. There is a challenge. I mean, I'm not saying that these aren't challenging things, but I think, as Vic said, if you put your mind to it, these are doable things. And I think it really, the dividend that you get, the benefits that you get from doing that are enormous. And so I think we should set our sights on being able to make that possible in geothermal wells. And I think the forge side, for example, like that you've been involved in, Rob and John, I think is a great example of trying to do these things and seeing how we can make them work and make them work better than we have in the oil and gas side at high temperatures.
Thank you so much. Okay, so I'm going to let you weigh in, and then I'm going to actually transition into, we're about on time, but we have so many great questions coming, better than the questions I kind of came up with for to start this panel. So, Susan, yeah, go ahead, and then we'll transition as soon as you finish.
So the wells that we produce in our natural geothermal systems typically produce 100,000 barrels a day or more, but they have to do it with a fairly low pressure drop. So when you're fracturing at those high rates, you are putting a lot of pressure on that because there's a lot of pressure drop involved. And so we have to flow these high flow rates with low pressure as long as we are at these around 200 degrees C kind of temperatures. But if we go up to temperatures greater than 450 C, at these high temperatures, the energy density is so much better and the conversion efficiency is so much better. We can get 10 times as much out of the same flow rate. So we're looking at being able to go from producing 5 to 7 megawatts out of a well to be able to produce 40 to 50 megawatts a well for the same flow rate. That's why we want to go to these very high temperatures.
And Isabel, I see you nodding and agreeing with us very, very animately. So I'm going to let you have the last word on this question, and then I'll transition.
Yeah, I fully agree. I mean, you have so much, it's almost, I mean, I'm not going to say it's going to be easier, but as Susan said, the energy that you can get from higher temperature, and when I say higher, I mean above 350 degree, like those high temperature, because your thermal stimulation is going to be more efficient. As Susan said, you're going to thermally, during the drilling, you're actually creating some fracture that will be useful. So it's almost like, why restricting ourselves to 200 degree at that point? If you have the resources to go higher in temperature, I will be with Susan on that and say drill hotter.
Thank you. Okay, I'm going to transition now to some of the audience supplied questions. Keep them coming, please. I don't, by the many of the great questions that have already been filtered and forwarded onto me, I already know we won't get to all of your questions, but keep them coming. This is something that us as a group, and maybe we can even come back later and have another discussion. But the first one I'm going to bring up is from Matt, and I'm going to do these in the order that I got them. So if you're popping questions there now, I really can't scroll through and see what the most recent ones are, but I'm going to try to keep up as much as I can. So the first question I'm going to pose, and it's timely. It's from Matt. It says, what is the biggest difference in hydraulic fracturing for EGS versus oil and gas? Do the skills and knowledge transfer directly? And I'm going to push this question first to John, and then I'm going to ask a few other panelists to weigh in.
Well, let me tell you about one of the fractures that was done in Fenton Hill in December of 1983. And that was a treatment that was done at 50 barrels a minute, high rate, like what we do today, or moderate rate. It was high rate then. That treatment lasted for 60 hours, and it pumped slick water. Sound familiar? And it pumped fine-grained calcium carbonate as a fluid loss agent and as a propant. So, things haven't changed a great deal.
Nicole, you're laughing. I think you rolled backwards in your chair when he said some of that. So, what are your thoughts here?
Oh no, I think that I agree with John that there's a lot of commonality between what we do in oil and gas and what we do in what we would like to do in geothermal. I think that the points that were brought up in terms of high rates and so forth are good points, and I think we need to figure out how we can achieve those things. Larger well bores may well be required, and as Susan was mentioning, but the key differences between oil and gas applications versus geothermal applications are, in oil and gas, you don't want to connect the well bores. You want to drain independent areas of the reservoir. In geothermal, you want to connect these, and you want to connect them fairly well across the entire lateral, which is exactly the opposite of what you're trying to do in oil and gas, right? You want to have pretty good profile control, and that's similar to what you want to do in oil and gas. You want to be able to, if you have 10 clusters in a stage, you want all 10 clusters to propagate fractures and not have a thief fracture that propagates. And that's similar to what you want to achieve in oil and gas. And you mentioned, Rob, limited entry, but there's other clever techniques that you have that you can do to try to prevent that from happening. And there's techniques you can do to make the profile much more uniform. So there's lots of similarities and a few differences.
Thank you, Mukul, or I'm sorry, Vic. You want to chime in?
Responsive to the question, hydraulic fracturing trained engineer walks right into the enterprise and goes to work the first day. Okay, the training is exactly the same. The only difference in the back room where they do the modeling to say, okay, I want to create a frac head, I want to do things different, but that is what the modeling does. Then it informs the operation. The actual execution of the operation is identical. So as far as the hydraulic fracturing, if you will, if there's such an animal, engineer goes. So these people who are currently out of work walk straight in and go to work.
Very good, very good. I want to come to another question here. I'm not sure, it's unattributed, but and the question is, what are the most urgent technical challenges to solve that oil and gas professionals could transition and collaborate? How can they help? Vic, I can right back to you. I think you're already starting to weigh into that, but can you want to elaborate further in that context?
Is this for me?
Yes, sir.
Okay, yeah. So go back a little bit to say, to Isabel's point, now why don't we just go to 350C? If you want to get the oil and gas industry as a whole, operators and service companies really into the game, you've got to get them going in volume on something. And that volume has to come from 200 degree stuff. Your 350 degree stuff is some ways away. So I'm saying baby steps, well, it's not baby, these are pretty big steps too. 200 degrees C, get going, get volume, get the industry comfortable with the notion, keep doing research, because the closed loop under supercritical is going to need research in materials, reeds, and bits. It's going to need research. And so I'm just saying it's a stage thing. It's not either or. It's a question of staging.
Very good. Thank you. I want to transition to another question. Or Sue, did you want to weigh in?
Yeah, I just wanted to say that, if we people keep talking about 200 degrees C. Our most recent fracturing effort at Newberry was from 300 to 325 C. So, and in fact, we have a second well that we're looking at that has a bottom hole temperature of 348 C, both directionally drilled. And these, I think, are where we need to be going. If we concentrate on 200 degrees C, our energy density is really so much less that it's going to take a lot of fluid flow, and that's a tough challenge.
I don't agree at all. If you do multi-stage fracturing in 200C, you have natural fractures that propagate. You can get material utility scale electricity produced at 200 degrees C if you do it right. Now, I'm not saying you shouldn't do 350. Okay, I'm just telling you that if you do, it is quite feasible. And the point is, it goes back to what I was saying earlier. We need to map the subsurface. Say, I personally think there's got a lot more opportunity for something with 200 degrees C and natural fractures than with 350. But it's not an either or for me. It is simply a question stating, if you think you can do 350 in high volume today, go for it.
So your key point, Vic, is high volume. That's not high volume of fluid flow. It's high volume of mass of people getting engaged and getting into the industry.
The oil and gas people are not going to be interested unless it's scalable. They believe in scale. Okay. If you want the geothermal to be an effective portion of an oil and gas company's portfolio, okay, just like oil is or gas is, it's got to be at scale. They're not going to look at one or two wells here and there. That's not going to work. That's why I was cool on this until recently. Until now, I think it is scalable.
Very good. Thank you, sir. Another question, and this is it's a question about India's central basins. It says there's great heat flow but very tight rocks. Are these conditions suitable for EGS? I'm going to answer myself and say, just say yes. And we'll move on there to save the panel. And that's the beauty of all these technologies and that's what I like about geothermal. And I, in full disclosure, I led INL's fossil energy research for a number of years. And I'm very familiar with, some of the work for the fracking and reservoir development, oil and gas. But what I liked about geothermal is, I like seeing the drill bit turn, and the deeper you drill, the rocks get hotter. Maybe at different rates, but they get hotter. So you can find a resource anywhere. It's just a matter of how hard you have to work to get to it. So I'll move on to another question here. This comes from Matt again. Can you explain the advantage of horizontal wells as opposed to angled wells for EGS? I'm not sure who to point that to. I'm going to start with John, because I know you've been struggling with this in your current well design at Forge. We're not struggling, but considering. And then we'll open it up to the rest of the panel.
So, in a sense, high angle wells offer equivalency. They offer some advantages in terms of ability to fish tools, ability to run logs, and in an oil and gas setting, a horizontal well may have more advocacy because you might be trying to steer that well into a narrower zone. Whereas if you're talking about a geothermal zone and say it's a batholith or something like that that's moderately extensive, then you can get away with a well that has high angle but is not necessarily horizontal and drills faster and more easily. So maybe that is the differentiation is in terms of the thickness of the reservoir.
Okay.
From my perspective,
I see a lot. I see the panel nodding in ascension. So I'm going to move on to the next question. And actually, it was directed to Professor Sharma about reservoir stimulation. Is there software that can estimate thermal energy similar to Eclipse for the oil and gas industry? I have my own answer to that, but I might weigh in after you address it.
Yes, there is, and so you can actually build very general models that allow you to frack these wells in three dimensions after you've characterized the site, of course, and then be able to do thermal calculations in terms of injecting fluids and calculating what kind of heat transfer you're going to get through the fractures, multiple fractures in a horizontal or deviated well, and so forth. So the answer is absolutely yes, and you can do this with a geomechanical fluid flow compositional simulator that we have built here at the university in my group, and there are others as well. And I think Rob, you've been involved in some of that.
Thank you. And now comes for the shameless plug. I wonder if I get a chance to do this, but there is a lot of work being done in this area, especially in regards to the Forge initiative and the Forge program. We have a monthly or bi-monthly Forge modeling seminar, a forum. And actually, there is one this week. It competes with PIVOT, but I would encourage people to take a look at the Forge website, Utah Forge, from the University of Utah. And we actually discuss these kind of issues in detail on a monthly and a recurring basis. And it's open to the whole community. So much like this, we take questions and go back and forth. So I'm going to move on from there. Thank you for your answer. Next question is actually also directed to someone, and it says, Vic, you mentioned scalable and dispatchable. What do you mean by dispatchable in an EGS context? And Sue, I'm going to actually put you on the hook to answer this one as well.
What I mean by dispatchable is that you can produce electricity at a high rate that is sufficient to feed the grid that you're serving. But a more interesting aspect of EGS and dispatchability, unlike, for example, nuclear, is that it can also be load following. So in properly designed EGS systems, you can load follow. Load following means when the load drops, you can actually turn down the output of your well. Now your generator is a little bit, sitting a little less and more idle or whatever, but load following is a huge issue. So I think you can create enough load to feed a grid, you can do it constantly, and you can load follow. This is the key aspect of dispatchability that I'm talking about.
Thank you. Susan, you want to weigh in?
Yeah, so load following is indeed something you can do with geothermal, but when we talk about dispatchability, the problem is we can't turn it on and off. The wells don't like it, the generation equipment doesn't like it. But what we've been looking at lately is thermal energy storage to go with your generation. that would allow you to add extra heat at the time when there's high demand, and then just run the plant at base, what's coming out of the ground the rest of the time. And we think that rock is a great heat battery. So, well, I don't think we're there yet for storing heat in the subsurface, just because we don't have enough control over what's happening down there. I think we need to be working on that. And for now, we're looking at, thermal energy storage systems that use the box of rocks on the surface concept, so we can learn how to use that.
Thank you. Thank you very much. Next question. And actually, I am, since the questions are coming in so well, just so the audience members know, I am cherry picking some of these. We'll come back to some of the ones I'm skipping if there is time. So the next question I want to point towards Isabel. And it says the temperature or mapping temperature is not as simple as mapping gravity and magnetics. There is no surface instrument to map surface temp or subsurface temperature. What does this panel have to say about it? I want you to lead that off for us. And coming from I'm sure you're doing a lot of work in the TVZ, so I'm sure you have some very things to tell us.
Yeah, this is a really good question, actually, because it's very true. Without drilling, you can't map temperature, basically. And so we have some tool we're trying to use, for example, the geophysical survey, and try to better understand, your heritage, better understand the distribution of your temperature. The other tool that you may have as well is understanding in our system where we have where obviously we have magma at depths, so we're understanding how the heat transfer from this magma to the surface to have an idea of how you can. So there's a lot of modeling involved into this to try, but you're right, we can't, without drilling, we can't for sure know the temperature. It's not an easy tool. So the other way we're doing this is as well combining as much as we can all the geophysics with a stratigraphy that we can understand. And as such, we can understand as well what are the mineral reactions, which are really important to understand what kind of temperature dependence we may have as well in the rock. It is a challenge, but it's a balance between knowing exactly where you need to drill and reaching it for the good temperature. In our example, for the topovolcanic zone, obviously we don't have that much. We know that if we drill, it's going to be hot, more or less. So it's more a matter of permeability than a matter of temperature for us. Which is a bit different, but obviously if you're drilling closer to magma or specific thing for where we're trying to target, we need to better understand what are the temperature halo around certain area and why this is hotter than other. And it's a lot of modeling, that needs to be done. And if there is someone else I want to pitch in on mapping temperature.
Yeah, there's a few here, and one of the key, this question, I think comes about and really highlights one of the key challenges that geothermal face in comparison to some of the intermittent renewables like wind or solar. It's a lot easier to understand your resource if you just look at it. You can see if the wind blows or the sun shines. We have to do a little bit of work to understand what our thermal resource is. Sue, will you weigh in?
Yeah, so one of the, I think, promising techniques that we're using to try and understand where the heat is in the subsurface is passive seismic monitoring. And then again, as Isabel says, you have to do a lot of modeling to go with that, but we can use teleseismics and ambient noise tomography to begin to map high temperature zones in the subsurface. And we're hoping that this will also help us see where there are fractures that already exist. But this is something that's developing now. Thank
you. Next question. And this isn't addressed to anyone in general, so I'm going to throw it out there and I'm going to watch for reactions by the panelists. Will proppants be needed to develop EGS fracture networks so they'll stay open? What type of proppants will work? Nobody even got a look in their face there. So John, I'm going to call, actually did. Vic, weigh in for us.
I think this is, proppants are needed, in my opinion. but I think the newer understanding on proppants, and John referred to it a little bit, is that very small sizes can be floated in there. We probably don't need to use a lot of gel in your hydraulic fracturing fluid. What people will be concerned with is, will the proppants hold up at the high temperatures? Okay, and I think that while they're slightly challenging, I don't think it's a huge issue. So yeah, I think yes, they're needed, but I think we know how to handle it. I think Mukul is far more competent to answer this than me.
Well, there's you get the spotlight shine onto you, Mukul. You want to weigh in for us?
So it's a great question. It really is a good question, and I think that the short answer is yes. You do need proppants. I think it certainly makes the flow a lot easier. So depending on the temperature, you can go with sand or with some other ceramic type material at the lower temperatures. But certainly, if you go to higher temperatures, you would need something better. And we had actually worked on that some years ago, about 10, 15 years ago. And we've developed actually an alternative to sand, which is about twice as expensive as sand, which is not saying much because sand is literally dirt cheap. But you can actually get something that is petroleum coke is the product, and you can actually buy this in railroad quantities, very, very large quantities. And it is, since it's been calcined at 1200 degrees, it actually is very thermally stable. And we've actually measured the properties of this proppant in the lab and found that it's quite thermally stable. It's stable under mechanical stress. Its conductivity is lower than sand at very high stresses, but you can actually use something like this if you go to very, very high temperatures, like 400 C, for example.
Thank you. So Isabel, you being our geochemist here, I'm going to call you a geochemist.
Yeah,
I know that's not the correct term. Kind of, but
okay.
Knowing if sand is going to melt or if we're going to dissolve or talk to us about this.
Yeah, sand is definitely not an option because you're gonna saturate very quickly at high temperature. And one of the things that is challenging in geothermal compared probably to oil and gas is understanding the water rock interaction above 200. When you're at low temperature, things take some time. When you're reaching 300, 350, chemical reaction between your fluid and the rock are really, really fast. And we're talking weeks, we're not talking years here. It's not a geological time scale. So you can really seal, you're opening a fracture, but you can seal it very quickly. So I think it would be really interesting and promising if there is some proppant to actually test as well, simulated in lab. What are the effects in the rock? How fast they're gonna, coagulate? You're gonna create vein basically, and it's just for the understanding of how fast we can seal a fracture right now. We're also just quickly because it's a matter of we know that's happening. It's happening conventional when you're injecting. We do know that. It's a matter of being far away so you don't block your well. And I think the proppant, we still need a lot of research around that in high temperature to see what other chemical can, play on that, because I don't think we have a very good answer for now.
Thank you so much. I'm going to transition, and actually, it's a question directly to you, Mukul. Do you think the public will accept fracking crews doing a multi-stage fracking job? How can fracking become accepted to help transition to green energy geothermal? Yeah, that's a loaded question. I see your hesitancy.
How much time do we have here? No, it's a great question, and of course, as I mentioned in my introduction, some of the issues that go around fracturing is the social issues of social acceptability of hydraulic fracturing, which is a really important question. I will say the way I usually answer that in short is to say that no matter what we do in terms of producing energy, you have to do a cost-benefit analysis. And looking at the cost-benefit analysis of hydraulic fracturing or the use of fracturing in geothermal, I think we can make a case, and we need to make a case to the public, that this is something that would benefit us greatly. There are risks, of course. There is nothing that we do that doesn't have any risks. But I think on balance, looking at a cost-benefit analysis, it's very clear that hydraulic fracturing and fracturing applied to geothermal has tremendous benefits, and I think that's really the way to put it to the public.
Thank you so much. Vic, you have a comment?
Yeah, quick comment. Hydraulic fracturing in oil and gas has a couple of issues that the public objects to. One is the possibility of hydrocarbons coming up through the return fluid and doing bad things. Well, there are no hydrocarbons to come up in this case. That's point one. Second thing is they don't like the fact that breakers and all kinds of chemicals are used in hydraulic fracturing normally. It may be possible in this case if you use small enough proppants, particularly if you use something like fly ash, which, by the way, will survive high temperatures, and which has been done recently. Then you could probably float this sucker in almost on water, and so you don't have a lot of gel. You don't have the kinds of chemicals that people are worried about. And then finally, if you do take advantage of natural fractures, then the energy to open a natural fracture is much less than the one to create and open a new fracture. And so the induced seismicity, which you kind of mentioned, one of you mentioned very briefly in the beginning, that concern will be heavily mitigated. I mean, nothing goes away. And as Mukul said, there is no enterprise without risk. But I expect the likelihood of induced seismicity to be far less if we do this, well, EGS type with natural fractures involved. So it is hydraulic fracturing, but it's not quite the same.
You know, that you mentioned a few things here, and it kind of leads into a few other questions that came in. And the question I'm looking at now is, how can seismicity be managed, particularly with high flow rates? This is a severe concern in Europe. I have my own opinion. I think I will weigh in on it, but I'm going to actually put it out to the panelists first. So, John, can you weigh in for us on that one?
Well, you know, the first key to this goes down to understanding the geologic regime that you carry out the stimulation in. You know, ideally, if you're in an extensional environment, and as Vic said, if there's natural fractures, then you have some things in your favor. If you're treating in a strike slip or a reverse faulting regime, then you have to be more careful, and you have to have the contingency programs dialed in up front and the stakeholder enfranchisement to proceed ahead with all of this, and then you can manage it.
Thanks, John. So for my thoughts here, you know, I see a lot of the concern comes up from induced seismicity when you think of the fracking term from oil and gas industry, or it could even be from, you know, large scale disposal of fluids, where in geothermal, especially, you have a multi-well system, or I won't say a closed loop of one form or another. If it's two wells with a fractured network between, is that we should be actually depressurizing one side and increasing the pressure in others. So that could help some mitigation for how far out or how far we interpret, or how far out away from those wells or we perturbate the stress fields. Vic, please.
Yeah, so I want to build on your point. In hydraulic fracturing enterprises, the seismicity, induced seismicity, has been from disposal of waste fluids. This will not be the case here because they will not waste fluid disposal that day. So that point I forgot to make, but thank you for making it. So I think that in principle, here it goes. You got to have an active fault. An active fault is one that when you put energy into it, actually slips. All right. That active fault has to be of a certain length, because the amplitude of a seismic event, or an earthquake, is directly proportional to the length of the active fault. So, and as John pointed out, you can detect these things. Okay, and so maybe, and I'm going to use the R word, maybe it's got to be regulated, but I won't use the word, so I just took it back. Okay, but I think good operators should take a look at it and make sure that there are no active faults of reasonable length close by. Okay, so I think there are measures that can be taken. They don't have to be as much as necessary when opening up natural fractures, but be that as it may, we must keep our eye on that ball, because that is one of the things that the public is concerned about.
Thank you so much. Sue, you want to weigh in?
Yeah, so induced seismicity is, and you do indeed need a big fault. You can't get a big seismic event without a big fault, but they don't need to be active, unfortunately. So the Rocky Mountain, I worked on the Rocky Mountain Arsenal induced seismicity from wastewater injection, and that was not an active fault. It was not a fault that had seen any seismicity in any time that had been recorded. Whereas you do need to have that big fault length. You can't get a big seismic event without it. So we have to have methods that map all the faults and fractures in the area as best we can to estimate our risk of induced seismicity. And doing that seismic risk hazard analysis is really important ahead of any kind of long-term injection without production.
An active fault is not only one that has just had an activity. An active fault is one, when you put energy into it, it'll slip.
Panelists, I want to thank you. Unfortunate, there are so many good questions and the discussion is lively, but I've been warned that we are essentially over time. I know, thank you for your passion here. And I want to thank all the panelists. This was a great discussion. I want to thank the audience for joining us today and posing such great questions to help invoke this great discussion. And please, those in the audience, please join us for the rest of Pivot 2020. We have great session lined up all week long, and you'll be seeing those here coming up really soon. So thank everyone. Thanks to our panelists, and look forward to seeing you in the future sessions. Bye now.